First of all, thank you all so much for having me. This has been like an amazing day of science so far. There's been so many interesting topics, and you guys are doing amazing work here at Maryland. And I don't know why it's taking me so long to come here and talk to people. There's clearly a lot of overlap. So thank you so much for having me and coming to my talk. So thank you, Mahan, for the introduction and the invite. So I'm talking about melt focusing beneath mid-ocean ridges. This is kind of like a labor of love that I've been working on for quite a while and continuing to work on. So I say implications for the LAV because people always ask me, why should we care about melt focusing beneath mid-ocean ridges? So I'll show that as I move along here. So I'm a modeler. I'm not, maybe a modeler. I am a modeler. So I solve equations. Modeling is very useful when there are places that you go to that you cannot directly sample, or you're going back in time where you definitely, it's very hard to sample anything back in time. So this is when modeling is very useful to understand theoretical processes. And there's many of you in the audience. So I'm interested, at least on Earth, at tectonic boundaries. Why tectonic boundaries? One of the questions that I'm really interested in going back early Earth is trying to understand how continents have formed and how that has co-evolved with plate boundaries. So today I'm just going to be focusing on mid-ocean ridges, so the Mid-Atlantic Ridge here, East Pacific Rise that's commonly talked about, and up there in Gecko Ridge. So at some point, maybe I'll get to answer those questions. But today, I'm going to be talking about mid-ocean ridges. So here you can see mid-ocean ridges are kind of this bathymetric highs on the ocean. You can see East Pacific Rise here. That's one of the fastest spreading. And then Mid-Atlantic Ridge here. And they are very prominent features on the ocean floor. So one of the traditional view of how this melting occur at mid-ocean ridges that forms new oceanic crust is by decompression melting. So you pretty much get two oceanic crusts that's kind of pulling apart, and by conservation of mass, you kind of need to pull stuff to fill that in, and so you get decompression melting right here in the center. So one of the characterization of mid-ocean ridges is that since plate boundaries kind of move at very different rates, you expect that this mid-ocean ridges spread at very different rates. So here I'm showing kind of the half spreading rates at all these mid-ocean ridges. And people tend to to categorize them in ultra slow, slow, and intermediate and fast. And all these numbers kind of differ depending on who you talk to. Some people like to place the numbers at different places. But really what it tells us is that, at places like East Pacific Rise, it's spreading the fastest. And then at places like Gecko Ridge, it's really spreading at very slow rates. And perhaps that can tell you something about what's going on at the plate interface and what you actually see on the surface. So one of the very important observations that's done at mid-ocean ridge is trying to understand what the oceanic crustal thickness is. And so this has been measured by seismic reflection amongst other geophysical methods. And over here, I'm showing a very classical data set by White et al. 1992. And what you see here is that at above 1 centimeters half spreading rate, the oceanic crustal thickness is fairly constant, right? And so that's kind of surprising given that they have a lot of different spreading rates. And you can see on the right here, what I'm showing is what that roughly 7 kilometers consists of. So if you were to go to the ocean floor, what you see, if you can see anything because it's very dark, the top will be a pillow basalt, and below that sheeted dike complex. Then you get to a gabbro and the layered gabbro, and that consists of the oceanic crustal thickness, crust. And then below that, you have the upper mantle. I mean, if we can drill here, it would be really nice. I think, Val, we were talking about that. It would be really nice to drill down there and see what's actually there, instead of having to rely on ophiolites and things like that. So this is a very fundamental observation for mid-ocean ridges. Well, for oceanic crustal thickness. So another interesting observation at mid-ocean ridges is that the oceanic crust is really formed within a few kilometers of the ridge axis, regardless of spreading rates. So regardless of spreading rate, they all the lava erupt within a few kilometers. The only difference there is really when you look at a slow spreading rate like a gecko, it looks very different. It's kind of an axial low valley where the lava is erupting, as opposed to when you go to East Pacific Rise, where spreading rate is really fast, you kind of get an axial high. Everyone can hear me, right? Okay, yeah, I'm pretty loud, okay. So you might expect that with like a pretty narrow region of oceanic crustal formation, you may expect the melt below to be pretty narrow. In fact, that's not what it's observed, at least not in this area, in the East Pacific Rise. There's been pretty wide regions of melt that's interpreted at depths. So here on the East Pacific Rise, I'm showing two surveys, one for seismic tomography, that's showing, phase velocity that is suggested to be melt. That's relatively wide. So before, remember that the oceanic crust is formed at a very narrow region. So the expectation is that, okay, maybe melt is just formed in a very narrow region. But here you're seeing it to be, maybe that's not true. It's probably pretty wide. And then in another place in the East Pacific Rise, you have magnetotelluric inversion, which is just sampling the resistivity or the conductivity of the mantle. And that's showing a very strong conductor at depths and pretty wide as well. So what you have here is that melt is generated in a relatively wide region compared to that very narrow ridge axis where oceanic crust is being generated. So while here we have a kind of a little bit of a problem, you have melt that's generated at a wide region and only a narrow region where oceanic crust is generated. So there has to be some kind of mechanism that's kind of focusing this melt to the ridge. So what are those mechanisms? So there's been two kind of classic mechanisms that's been proposed. At least these are more well-established mechanisms that I'm going to be talking about today. One is ridge suction. So you can imagine that when you have incompressible shear, you're pulling apart two strong plates. You're essentially creating like a suction right at the ridge axis, and that's kind of pulling melt towards the ridge axis, right? And that's been like put out by Spiegel and McKenzie 1987. And then on the right here, some of you might be familiar with this decompression layer, or what we can also call an impermeable barrier, where you have a plate cooling that's thickening with age away from ridge axis. And so that creates kind of like a natural sloping boundary where buoyant melt that's created over a really wide region just buoyantly rises, kind of like gets to this boundary and gets channeled to the ridge axis. So these are the two mechanisms that's been put up that's pretty well established. So today I hope I'll convince you that on top of those two mechanisms that you can see from the two-phase flow equations, that there's another one that we recognize at least, that's called melting pressure focusing, and that's happening deep in the melting region. So on the left here, I'm kind of showing previous models, including Laurent's work that shows decompression channels up here. And then 3 is kind of the ridge suction force that I was talking about right at the beginning. Right, so I am a modeler. I work with equations all day and every day, and that's my bread and butter. I really enjoy working with equations. So when we think about two-phase flow, well, let's take a step back in terms of, and think about what geodynamics usually use. Typically, in a single phase flow, you conserve mass, momentum, and energy in the solid form, right? But in a long-term fluid. So in a two-phase flow, you kind of have to do that, but for two objects of very different viscosity. So one that acts more like a solid and one that acts more like a fluid. So in this case, the solid here is the mantle, and then the fluid is kind of the melted mantle, which I'm going to call melt from now on. So here you need to conserve mass for both the solid and fluid, and momentum for both the fluid and solid, and we kind of have a aggregate conservation of energy for both of them together. So I have to show you some equations because that's what I do, but then I don't need you to look at this and there's no quiz at the end of this, right? So I just want you to focus on the fluid conservation momentum here, which is in the two-phase flow community known as the Darcy's. Well, it's kind of a Darcian flow. Essentially, what is in this equation is that you have phi, which is a porosity or a melt fraction. And here we are assuming that any melt takes up all the pore spaces. There's no air and there's nothing else. It just takes up the whole pore space. You have Vf, which is the fluid velocity. Vs is the solid velocity. So this is just a melt separation, segregation kind of flux. And on the right here, you have the K, which is permeability. And then mu, which is fluid viscosity. And then you have a pressure gradient on the right there. So this just tells you that melt tends to segregate from the solid because of a pressure gradient that's modulated by the permeability and the fluid viscosity. And over here, I'm showing you what that melt might look at. Thank you, Wenlu, for creating this beautiful image that I can show here. So the empty space is just kind of the solid aggregate, and the gray and red is the melt here. So before I can do this work, I have to make sure that melt can actually flow in kind of a Darcian way. So thank you again, Wenlu, for doing this amazing work. I really appreciate it. So the point of this slide is really, showing, maybe Wenlu you can talk about it. But from A to D, this is increasing in porosity. And this just goes to show you that even at very low porosity or melt fraction, you have pretty good connectivity, which shows that it's possible that you have a good permeability there, right? So here it gives us some confidence that, okay, you might have a pretty efficient melt transport at pretty low melt fraction, which is good for what I do because I am looking at, melt flow through a mantle matrix. So when we are talking about melt flow, it's really the pressure gradients that pushes this melt flow, right? Melt flows due to pressure gradients. So what helps us to understand this is to break down that pressure, which I show at the Darcy flow, which is the equation. Maybe I should write that down, but in a little bit. So you have the total fluid pressure. We have broken it down to compaction pressure, lithostatic pressure, and dynamic pressure. So dynamic pressure is just you have these two plates that's moving apart, and that pressure really comes from the solid, incompressible shear. So that is kind of what's creating that pressure right in the ridge axis that's pulling melt towards the ridge axis. And then you have lithostatic pressure, which is pretty much what's on top of wherever you are at in the domain. And then compaction pressure here, I've shown down here. It's pretty much the divergence of the solid velocity that's scaled by the bulk viscosity. So you can think of this as the expansion and contraction of the solid matrix. So a good way to think about compaction pressure is kind of like a sponge, a wet sponge. So if you take a wet sponge and squeeze it, the water is going to come out, right? And then if you release a squeezed sponge in the water, and it's going to soak up the water. And the bulk viscosity, you can think of it as how hard it is to squeeze the sponge. So is the sponge like a loofah, or is it like, you know, a very tough thing? So keep that in mind when we are thinking of compaction pressure, because that's something that's important in moving fluid around. So now when we put that equation, this pressure decomposition back into this Darcy flow, you have that melt segregation, which is, again, like the melt fraction, and this is the solid velocity VF, and the fluid velocity VF and the solid velocity VS. And that's kind of pushed by all these different pressure gradients here. And we'll revisit this down the road. So now I'm going to talk about the two different melt focusing mechanisms in terms of the pressures that I just talked about. So first of all, we have ridge suction, which, remember, over here we have like two plates that's pulling apart. So you have that dynamic pressure that's coming from the incompressible shear of a pretty strong lithosphere, right? So you have that it's kind of pulling melt from around, whatever melt that's around, within a certain length scale towards the ridge axis. And that's kind of what they were talking about in that paper. And that's why there's a length scale that's associated with it. So for a decompaction layer, it's essentially due to the compaction pressure. So you have a pretty weak mantle with kind of higher permeability. And you have buoyant melt that's generated in a pretty wide region that's kind of just moving up. And it encounters a strong lithosphere that has low permeability, so melt cannot go through it. So it kind of forms this layer here. The decompression pressure essentially pushes melt away from this strong lithosphere and creates that decompaction channel to form. And because it's slanted, it moves the melt buoyantly up towards the ridge axis. Oh, crap. Okay. So I'm going to roughly go through the modeling details, but then if you have any questions, please feel free to ask. So I'm going to be showing you the models that I've been doing. They are a rectangular domain where the ridge axis is on the center line. And the top of it is the moho, so it's below the crust, right? So I'm only modeling all the ductile material. And this box is kind of 100 kilometer deep and 200 kilometer wide. So what I've enforced on the bottom and side boundaries is there's no parallel flow on the bottom and the side. So that essentially creates an inflow boundary on the bottom and an outflow to the side. Essentially, you have two corner flow, right? And then at the top, and that's pretty much because of boundary condition at the top, where I enforce a half spreading rate on either side. And the blue triangles are the mesh that you can see here. It's a lot finer at the ridge axis because that's where we expect very high pressure gradients. So we need higher resolution to be able to resolve that. And away from it is kind of coarsening because we don't want to have to deal with calculating so many numbers. And we don't expect the pressure gradients to be very big out here. So it's about 8 kilometers, I think, out here, and about 100 meters up here. And this is all done using terra firma, who is kind of worked on by Kian Wilson and Mark Spiegelman. So Kian is actually at Carnegie as well. Like if you guys are interested in using it, it kind of leverages open source libraries like Phoenix and PETSI and SPUD. If you guys are interested, please talk to me more about it. So before I actually show you a video of what the models look like, I want to go through what you will be looking at. So this is a model snapshot. So this is, again, 100 kilometer deep, 200 kilometer wide. And then on the right-hand side, you'll be seeing porosity or melt fraction, right? And those are, let's say, 0.04 will be 4% volume fraction melt. And then on the left-hand side would be compaction pressure. Remember, this is just a divergence of a solid velocity that's modulated by the bulk viscosity. So expansion and contraction of the solid matrix to either let melt through or for melting to occur. And the melting occurs at about the dry solidus, which is roughly like 60 kilometers in this case. And the white lines are going to be melt flow lines. And in this case, it's kind of flowing up along this line. And the time given here is non-dimensional time. And for this case, which is the slow spreading case, so half spreading rate of 2 centimeters per year going either side, gives you about t equals to 90,000 years. So the full time for this simulation that I'm going to show you is about 27 million years. All right, hopefully this works. It's supposed to. Right. Let's see. So this is kind of a slow spreading case, and that should, represent a place like mid-Atlantic ridge. So again, on the left-hand side, you have compaction pressure. On the right-hand side, you have porosity or melt fraction. And you can see right at the very beginning, there was kind of a transient period of time. That's just how long it takes for the model to kind of come to a quasi-steady state. And when I say quasi-steady state, it's clearly not exactly steady state because there's all this time-dependent porosity waves here. So I want you to notice kind of two things: where the location of the melt is and where melt is kind of flowing. So the thing you notice is that there's melt right in the very center part. That's melt rich. And then also it's melt rich on the porosity waves. And that's kind of accumulating beneath this like strong and colder lithosphere. So that's where you expect like the decompression layers to be. And you also notice two different melt transport patterns by looking at the melt flow lines. So in the center here, you kind of see kind of horizontal flow that's moving melt deep in the melting region towards the center on the ridge axis. And then it's kind of moving up. And away from the ridge axis, you have this more vertical flow lines you see melt moving up buoyantly and then moving up into this porosity waves. Yeah, so this goes on until 300. And then now, I'm going to show you a set of models. And at the end of, pretty much a snapshot at the end of this movies that I've shown you. So the top right here is what you all were seeing in the previous slide. And I show you that because that's the more interesting one in terms of time series, because the rest of them just stays like exactly what you see in this snapshot for after the transient period of time. So it's kind of boring. And it's interesting here only because of the porosity waves. So what I've done here is to change the half spreading rate, which is increasing down here in the rows. So the top row here is for 2 centimeters per year, going up to 8 centimeters per year. So this is half spreading rate, meaning that each side is going at 8 centimeters per year. And on the left column, we have intrinsic permeability that's lower than on the right side. So on the right side here is higher. And that just means that when you have higher permeability, it just means that all the melt that's being created is more connected. And so a lot of melt can go through faster. So you expect less melt to be retained when you have higher permeability. And that's kind of exactly what we see in these models, right? In this snapshot, is that, again, on the right panel of each of these models is porosity. So the expectation is that the melt here in this column is much less than here, which is exactly what we see. And the two things that you can notice is where the melt is, which is in the center region. It's a little bit hard to see here. There is like a higher melt right in the center. It's clearer for the higher permeability cases. And they're also on the decompression layers. So for both of these cases. And then also the melt transport, you can see here there's two patterns. They're a lot less focusing right in the center for the lower permeability case, which I'll talk about in a little bit. Most of the melt is kind of only traveling upwards and focusing by these decompression layers. And then when you look at the higher permeability case, you have a lot stronger melt focusing in the center. So that's when like a melt is kind of being pulled horizontally in the center. And then away from that, it's again like buoyantly rising and moving into the decompression layers. So right at the very beginning, I said that one of the fundamental observations at mid-ocean ridges is the crustal thickness. Well, not just at mid-ocean ridges, but ocean floor in general. So one of the proxies that we want to get at is how much crust are we actually forming out of these models. So we had two ways to do it. One is taking the total amount of melt produced and seeing how much crust you can form over time. And also number two here is melt flux. So at the top boundary, we are looking at how much melt is actually coming out and seeing how much crust that actually forms. So plotted here is for all the different spreading rates, the total melt that's produced and how much crust that will form. And then on the bottom here is the total melt flux that will form oceanic crust. So you can see they kind of go into a quasi-steady state except for this like very squiggly line, and that's where you get the porosity waves. So you can actually get a funny modulation here for this particular model case. And you can also see that there's an offset between crustal thickness that's generated by the total melt produced and the crustal thickness from total melt flux. And that's because not all the melt that's produced due to decompression melting actually makes it out to form oceanic crust. Some of it actually freezes into the cold and strong lithosphere, and they kind of just move away with the solid. So that's where you see this offset here. But it's not, it's about 1 kilometer, give and take. So what we can do here is then to average like those numbers after the transient period of time. And so here on the y-axis is the mean crustal thickness that I've pretty much averaged from the last slide, and then plotting against the half spreading rate. And I've also plotted with the models like the White et al. Compilation that I showed at the very beginning, and also a more recent compilation by Harding et al. 2017. That's a lot more data that they collected from a seismic reflection, I believe. So that gives you a clear idea that this is not just those black squares. It actually looks like the average crustal thickness was kind of lowered by about 0.5 kilometers or so. And also you see variability that's becoming less as you increase in spreading rate. So in terms of, the triangles here are the average from the total melt produced from the models I was showing in the previous slide. And then the circles are from the melt flux. So this offset here is pretty much that freezing I was telling you about. But what I really want to emphasize here is that, this for us is kind of a validation step because we want to make sure that we are producing the right amount of oceanic crust. since that is one of the few things we can actually observe, right? Like, and actually get from the models. So now I'm relatively happy with my model. They are producing the right amount of crust. So maybe you can go ahead and look at the focusing that we are interested in. So melt focusing really depends on, melt moves because of pressure gradients. And focusing can only occur because of horizontal pressure gradients. So when I was talking about rich suction, that's because of dynamic pressure. So I plotted here on the left is the dynamic pressure. And you can see that it's pretty small. It's there, but it's pretty small regardless of spreading rates. And it acts only within a few kilometers of the ridge axis. And then when you look at the compaction pressure, you kind of have two regions. You have close to the ridge axis here, strong gradients, and also on the decompaction layers. So what you notice here, the difference between higher permeability and lower permeability is that it's a lot stronger for a higher permeability case. And so I'm going to try to convince you that this is actually a very straightforward things that come out of the equations. Hopefully this is right. So one of the things that we do is conservation of mass. And when you have a quasi-steady state, can everyone see? Everyone can see? Okay, good. Oh, I think everyone can see, right? So this is kind of the conservation of mass bit of things. This is material derivative. And, oh, there's a minus sign here, right? So what happens here is that at quasi-steady state, you kind of take this away in the frame of the solid. And remember that the compaction pressure is just this, right? Like your divergence of solid velocity that's modulated by your bulk viscosity. So when you put it back in here, you pretty much get that your compaction pressure is equivalent to your bulk viscosity modulated by your what is it called? Melting, and density is not going to change too much. And in the case of what we are doing, your bulk viscosity is actually your shear viscosity over porosity. So what you're seeing here is actually just a very straightforward, mechanism that comes out of the equations. It's really this compaction pressure is due to this melting region. And the melting region is going to be all the same because it's all the same solid uprising, right? Like the decompression melting. And then that's modulated by the bulk viscosity, which is just a shear viscosity over melt fraction. So in this case, because the higher permeability is going to retain less melt, your porosity is much smaller. So your bulk viscosity is a lot higher. And that's why your compaction pressure is a lot higher on the right-hand side when you have larger permeability. And that's exactly the effect we see here. And it's really nice that it just comes out of the equations. So now here, hopefully I'll try to convince you that another thing that can happen that you see here is that your bulk viscosity is also dependent on your shear viscosity. So depending on the kind of rheological laws that you're using, that is going to change your melting pressure focusing, which is what I'm calling this focusing that's kind of deep in the melting region. So on the left-hand side, so on the right center bit here, that is exactly the same model that I was showing you before in the panel of 6 models. And on the left-hand side here is just isoviscous models. So the whole domain has the same viscosity, shear viscosity. But they are kind of increasing in strength here. So up here is like the weakest at 10 to the 19 Pascal, and here is 10 to the 21 Pascal. So you can see here, as you increase your shear viscosity, you are increasing that melting pressure focusing. And that's exactly what's happening here, right? When you increase this eta, you're going to increase your zeta, your bulk viscosity, and you're going to increase that pressure right in the center. And that's, and because all the melting is the same, that remains the same, right? Gamma remains the same. And you can see right here that in the second panel, it only happens within the melting region. Because without melting, it just doesn't care about it. And on the left here, they're all isoviscous case. The Earth is not an isoviscous ball of fluid. So on the right here, that's why we put in some plates and string at the top. So on the top here, if I were to change the shear viscosity to diffusion and plasticity without this location creep, so kind of like taking away that 2 weak lobes that this location would do, you have melting pressure focusing that's happening throughout the whole melting domain, as opposed to here where it's happening in a pretty smaller region, right? And if you do increase like the stress exponent to kind of emulate a grain size evolution case, you don't see too much of a difference from if it was smaller. If you guys want to learn more, talk to me about it. I can go on forever about this. So hopefully I've convinced you that on top of like rich suction force and decompression layers, you can also have this very prominent melting pressure focusing if you include viscous compaction of the solid matrix. So why do we care, right? Why do we care about this? Why does melt focusing matter? It matters because it really tells us where melt should go, right, beneath the mid-ocean ridge, and melt transport and melt. And in this case, this is a really nice figure by Carnegie. That's like a magnetometric study at the EPR that I was showing like right at the very beginning. That's showing a conductor right in the center, and that's they interpret that as melt to be quite a lot of melt actually. How much melt there is, I don't know. And then it's also pretty depleted and devoid of anything else on the side. So we can compare right away to our models and see whether they match or not. So the models do produce the observed high melt region. The amount of melt might not match absolutely, but this deep focusing actually coincides with that. And so maybe that's actually what's happening in terms of melt transport. But right away you see something really weird here, is that there's supposed to be a melt-rich region here, right? But you really don't see that in the MT. So what's going on here is kind of weird. And this is why melt focusing is very important, because melting pressure focusing, this mechanism I've been talking about for a little bit, it's the only mechanism that can focus melt before it reaches the decompression layers. So maybe we need that to be stronger, I'm not sure. But maybe also so this is, we want to figure out where is the LAB because there's some disagreements there. But we also want to figure out, are the geophysical methods just not picking something up? Or the models are lacking something? How can we reconcile this, right? So I'm trying to work with seismologists and electromagnetists to try to figure out, okay, if you were to take my models, what are you going to see? What should you expect to see? So first of all, I can do not me, but my favorite electromagnetist is going to do this work, right? Like for EM, get the conductivity, and then get the empty synthetic data, and then invert that to see if you can actually see the decompression layers. And then do the same for seismic and pick your favorite parameter, right, in terms of seismic. So this is pretty cool, relatively new stuff that that I've been trying to get people to help me with. So here I'm showing the smaller permeability case and the larger permeability case. And this on the right, it's the EM resistivity that you expect just with the forward modeling. So this is just the first step of doing this. Hopefully we can then get the synthetic data and like see if you can actually see that. So you already see between a small and large permeability case whether it can match like what we see in nature. Hopefully at some point we'll figure it out. And that might tell you something more about whether we have gotten like the shear viscosity of the mantle. Maybe that's a little bit off. We could have to rethink that, and that would change the melting, whatever melt focusing is happening there. So another thing that's like really exciting that, I don't know how much time I have actually. Just a little bit time left?
6 minutes.
Okay, cool. So another thing that I'm really excited about is the porosity waves. You can see from the videos that there's this time-dependent things. And I've been trying to I have been working with Ross, Pernell Turner, and Jean-Arthur Olive to try to figure out how it correlates with seafloor bathymetry. So very quickly, this is like things that's hopefully about to be published, I'm not sure yet. So this is bathymetry at the south East Indian Ridge. And this is actually data from the Malaysian airline search, which people talk to me about, and it's very upsetting. At the same time, I'm glad some science is coming out of it and that I'm part of it. And so on the right here is the spectrum. So the black is the from the bathymetry, and the red is the mantle Bouguer anomaly. So then I can do a model that's like similar to the spanning rate around there, and it's about 3.5 centimeters per year. And what you can see here is like, you do get porosity waves. I was a little bit skeptical about this at the beginning because I wasn't sure whether I was going to get porosity waves for this particular case, and because we don't know that quite well yet, right? And then the power spectra here is kind of this is what it is, and like you get interesting peaks that I'm not quite sure how to make out of them yet. But really, we do see like a long period that might help us explain this long period that you see at a corner frequency at the actual bathymetry. So perhaps like porosity waves could be giving you a different magmatic source for this bathymetry. So this is some of my conclusions. Melting pressure focusing is definitely a very robust mechanism, and intrinsic permeability is very important for this particular pressure focusing, and so is rheological models. And the dominant focusing mechanism really matters for trying to figure out, in principle, where the LAB or lithosphere-asthenosphere system should be. And something that I'm excited about is like porosity waves could really contribute. This is long periodicity that you see on the ocean bathymetry. And this is just one example, right? I could apply it to across the ocean and see if this actually matters or not. But we do need the very high resolution data, which is quite lacking. So all this, I talk mainly about modern Earth, and like I'm actually really interested in early Earth, and I know maybe someday I'll get there. And talking with all of you have been very inspiring, like to help me think about early Earth and exoplanets. So changing the different parameters to kind of emulate like early Earth and also different planets I'm also working on more subduction stuff, which I've talked to some of you about, and hopefully at some point you see that work. So I think that's the end. Thank you so much. These are all my collaborators.
Is there some sort of serious trade-off that you have to worry about if you apply this to ultra-slow spreading ridges? Because I don't know that much about them, but from what I understand, they're pretty brittle and they like actually have mantle coming to the surface.
That is an excellent question. It's one of those things that I don't show you because I don't actually work on anything that's slower spreading than half spreading 2 centimeters per year, because all of them break. Yeah. All of them break because it's a little bit too cold, and it gets stuck, and you get crazy pressures that the models just don't like. And so that's something that I'm actively working on to figure out how can we solve this problem, because there's got to be a way to solve this. Yeah, so, stay tuned.
That's actually one of my questions
yeah.
as well.
Yeah.
Any other? Liam?
If you go back to the slide that you overlaid the model over the diagram of the ridge, the seismic diagram.
Overlay the ridge.
It was like you had a partially transparent view of your model overlaying that. Yeah.
Yeah.
Is the slope that you define for what would be the impermeable layer in your model, if you altered that to be more like what you would observe potentially in that image, does that change the model output?
No, so it's about the slope here is not too much, and it's the crust here is about 7 kilometers, so it's not going to change it too much.
Okay.
Yeah, I wish that was the case. Then it's like, oh yeah, we match it. Yeah.
So, as someone who thinks about fluid transport in subduction zones, I've heard talk of porosity waves. But as someone who looks at rocks, it's always been difficult to think of what I would look for in the rock record as far as seeing porosity waves or evidence for them in exhumed rocks from subduction zones, or even in active subduction. So it's cool that you can potentially see them in this setting. What would we be looking for, say, in a subduction zone if we were seeing porosity waves, whether that be melt or an aqueous fluid?
Yeah, I get that question a lot, so I really appreciate that you're asking it. So one of the things I can tell you is that you can't actually see the melt because it wouldn't be a rock, right, like that you pick up. But what happens is if I go back, let's see, to this, that becomes the question of freezing. Right, at this cold, strong, just cold, right? I don't have to keep emphasizing. There is freezing that's happening, and depending on that freezing and how that interacts with the porosity waves, that's going to give you a certain geochemical pattern right there. And so what I actually calculate from these models is the degree of melting that a parcel have seen. As it moves up and experience some melting and gets transported and experience some kind of freezing and moves out here. And so I can tell you that at least. So for a highly compatible element that stays in the mantle, I can tell you what that looks like, but that's very dependent on the freezing. So I can't tell you that if I were a very good geodynamicist, I'll tell you that, oh, this freezing model that I'm using is absolutely amazing. But I'm going to be frank and tell you that, yeah, we have to do a lot more tests before I can tell you, hey, just compare this to, can you pick up a rock and see the patterns there? So this is why I was very excited when I was talking to Val, okay, if you were to drill here, what is the pattern that you expect to see? Because I do have a pattern that my model predicts. Is that what you see? I don't know, because we need to drill, and we haven't done that yet. So maybe. So yeah, that's what I'll say you can see.
So Joyce, can you go over your main slide in a little more plain language, like using a sponge analogy? So you had the main factor being permeability.
Oh, okay, that one. I think this one?
Yeah,
Right? Yeah, so, okay, back to like the sponge analogy. It's, so you have a stronger compaction pressure here that's kind of pushing melt towards where it wants to be on a ridge axis, which is the, so in this case, your sponge right in the center is kind of trying to soak up, trying to push melt towards the center. So if you have melt that's created in this region, it's kind of like being squeezed towards the center. You can imagine like a really big sponge that's full of melt, and they have different varieties of holes, right? So you're just pushing it, and they're kind of like going upwards.
So what's pushing from the side?
This is like not a great analogy in the sense that like I'm making this motion of pushing from the side, but it's not actually pushing from the side, right? You have to think of it as a whole bunch of little sponge, and each of them is being squeezed at very different rates, right? And so all this little sponge is kind of making up this whole matrix. I'm not technically pushing it from the side.
So from what I understood was, so if you have a bunch of melt, right? So the whole thing gets squishy. You have a squishy sponge, right?
Right.
And so does that mean that when the milk gets out, the suction becomes bigger?
Right, so there's two things that's happening with the compaction pressure here. One is that there's melting. So if you don't think of like expansion and contraction of the solid matrix, and you just think of melting, so the melting is, when you start melting a puzzle, there has to be some kind of pressure that creates the pore pressure, right? You have to have pore pressure there to accommodate the melt. And then you also have this other, compaction pressure, which is kind of saying, okay, is my, the liquid overpressure more than the lithostatic pressure and the dynamic pressure? If that's the case, then maybe I should be expanding and then taking in more melt from elsewhere or something like that. So you can think of it as overpressure between the solid matrix and the fluid. Yeah. So it's, I guess in mechanical engineering, it will be more like a hydraulic head in some sense. So a pressure gradient between the two. Yeah.
Okay, so let's have a question from Lulu and Mark.
I actually am wondering, you must be able to have your compression-driven center. That's where you have more melt than surroundings, right? Do you know how much more melt you get?
When you say how much more melt, do you mean melting?
Because your
or?
new compaction mechanism, the third one, right, really gives you a way to focusing the melt at depth. I love that. So I'm asking you from your model how much you actually predict the melt distribution difference between where you see the compaction in the center and because they focus, right? So there has to be a heterogeneity in the melt distribution. So I'm asking how many percent of melt you would see in your model, not just in nature, but in your model. What I'm trying to get at is, if you actually have that, then we can try to think how much of a seismic velocity difference it would make. And I'm wondering why this type of deep focusing only observed in the electromagnetic measurements, not in the precise seismic measurement. Because they made a very clear comment in their paper that they do not need the heterogeneity with their other velocity data. That's what I'm getting at, because I think that's a very important thing that through this type of modeling we can test.
Right. So there's two things here. One, okay, if you have no melting pressure focusing, there will be just heterogeneous, right? And then you just have the decompression layers. Yeah. So then you can look at like what the difference is between right in the center versus like right here on the side, right? And so that's one thing. I mean, I don't have like a straight answer for how much. There is quite a big difference in terms of melt, like what you see here versus right in the center. It's like about an order of magnitude, like difference. So it should be pretty observable, right?
So that's what I'm questioning. Why,
Right.
if you actually can do that, you would be able to see seismically they are going to be different, right? And with that, all that's seismology studies, we don't see any need to actually model the data with any heterogeneities. So that's what, I'm not saying model, I'm just saying now we have a new tool to actually
Figure out.
test that.
Yeah, I absolutely agree. I mean,
I'm old school, and I still think that the seismic data tend to be a little more trustworthy than the magnetic data because of the inverse model is non-unique.
Right. I absolutely understand that. I mean, I absolutely agree. I mean, that's why I'm working with both a seismologist and electromagnetist to see what you should expect to see. And this is a good point, and that's something that I can definitely ask Kate. So I'm working with Kate Reichert. Ask her to do to see, okay, if I don't have this center part here, what do you expect to see versus taking the whole model like in point. That's a really good point. And I would think that you would be able to see it if it's like an order of magnitude higher. Yeah.
Mark, do you have a question?
Yeah, I was wondering, I was struck by the irregularity in amplitude and in frequency of the porosity waves. So is that just an artifact of the modeling, or is there some physics, some nonlinear restoring force that's at work there?
Right, so it really depends on, porosity waves are a natural consequence of this, the two-phase flow equations. And they really occur when your melt flux length scale is at the same length scale as the compaction length. And your compaction length is essentially, sorry, I'm like using up the board. So your compaction length is like related to your, it's kind of related to your permeability and your bulk viscosity over your fluid viscosity. So if, and this here is, what we are using here is this, right? And your permeability is also related to melt as well. So that length scale is what really determines like whether there will be porosity waves or not. And this is something I'm actively looking at because we don't really understand quite well porosity waves in this setting. I mean, I couldn't tell you that I would see porosity waves that's persistent. I mean, actually, all of these models, you see porosity waves right at the very beginning because they're a natural consequence of these equations. But whether they persist or not, that's a totally different question. And I was kind of surprised to see that, over here you do see that it's persistent throughout the whole model time. Yeah, so I hope I answer your question. We can talk more if you want.
Right, it's been an hour, so I think we can thank the speakers.
Thank you so much.